Okay, this is the last lecture covering projectiles. We're going to take a look at specifically 3 example problems. Let's take a look at the first of those problems. Copy it down into your notes. Prove that a projectile's range is maximized when the projectile is launched at a 45-degree angle. Now, if you launch a projectile from the ground like so, and you want to maximize the horizontal displacement, you want to maximize the range, at what angle should you throw the projectile? If I asked you this while you were sitting here in my classroom prior to actually tackling the problem, probably 90% of you would have intuitively have thought to yourselves, oh, throw it at a 45-degree angle. You're right, but that's what we have to prove here. So prove that a projectile's range is maximized when the projection angle is 45. Okay, so here's then what we have. We're going to be using our horizontal displacement expression and our vertical displacement expression. Notice, by the way, that I'm setting both y0 and x0 equal to 0 as I write these expressions down because I'm just going to launch the projectile from the origin. Okay, so here's what we have. Okay, we're going to launch the projectile with some speed v0. Here are the components of the initial velocity vector. Right here is the angle theta naught. Okay, we're going to launch from the origin, so both x0 and y0 are equal to 0. Okay, and then we're looking at a range situation. So the object returns to its original height, its final vertical position y is equal to 0, and then right here is the range x, like so. So another way of stating the problem is what we're supposed to do is prove that x is going to reach its maximum value when in fact the angle theta naught is 45 degrees. Okay, so how do I begin such a problem? Well, let's go ahead and take a look at the vertical position equation, and because we do in fact return to our original height, let's just go ahead and write the position equation as y equal to 0 and see what happens. Like so. Okay, and then the time t here is the unknown. There are 2 solutions for time. One of them is 0 because the object starts at the origin at times t is equal to 0. We don't care about that. Let's go ahead and cancel out one of the t's here like so. And then what I'm going to do with the expression that I have left is solve for t here and then plug it into here. Because when I do, I'm going to come up with an equation for x, the range that's going to be in terms of the angle theta naught. Think of this as 2 equations and 2 unknowns, where the 2 unknowns are time, which we don't care about, and the angle theta naught. So then therefore I'm algebraically combining the equations together in order to eliminate time. Okay, let me finish this process. I'm going to move the 1/2 gt here to the other side like so. Now I'm going to cross multiply the 2 and the g over to the other side to get the time t by itself like so. And then as I indicated a few moments ago, I'm going to go ahead and take this time t and then plug it into here to get an equation for the range x. Okay, so doing so, I'm going to now obtain the following. Okay, so x is equal to v0 cosine theta naught and then multiply by t, that quantity there. Like so. And now take a moment and stare at this equation carefully. Do you see a trigonometric identity? Let me rewrite the expression a little bit. Now the expression I'm writing down here is the exact same expression as the one above. I'm just moving the terms around a little bit more carefully. Take a look at what's in parentheses. Do you see a trig identity? Yes, it is the double angle identity for sine. Recall the following. The double angle identity for sine is as follows. Sine of 2 theta naught is equal to 2 cosine theta naught sine theta naught, like so. This expression right here that I've derived for us in the context of this problem is actually given a name. This equation is known as the range equation. Okay, you could directly apply the range equation for situations that call for it. You don't have to derive it every single time, but when you do use the range equation, you have to keep in mind that you're starting and ending at the same height. In this case, both y0 and y equal to 0, and then you can quickly calculate the horizontal displacement x by using this expression. So what I'm going to do here for the problem that we're working on is apply the range equation, and then I'll also apply it for a second example as well. Here's how it works in this problem. regardless of the value of the initial speed v naught, what we want to do is we want to make x as big as possible. Now, x is going to be maximized. It's going to be as large as possible when this term here, the sine of 2 theta naught, is as large as it can be. Recall from basic trigonometry that the largest number that the sine of an angle can be is 1. So in other words, x is maximized when sine of 2 theta naught is equal to 1. Okay, now the sine of what angle is equal to 1? 90 degrees. So then therefore is the answer 90 degrees? No, 2 theta naught is 90 degrees. Therefore divide by 2 and theta naught is equal to 45 degrees. So we've done it. We have now proven that the range is maximized when the projectile is launched at a 45-degree angle. Okay, let's take a look at a second application example here of the range equation. I'm not going to rederive it. We're just going to use it directly in the next example. Let's take a look at that now. Okay, so let me read the example to you, copy it down into your notes. A bullet is fired at a target at the same height, a distance of 100 meters away. The bullet's initial speed is 380 meters per second. That's a realistic number, by the way. It's above the speed of sound. At what angle or angles should the gun be aimed in order to hit the target? Okay, let me do some erasing here. Okay, so here's the problem. Okay, so we launch from the ground like so at our V naught of 380 meters per second. Okay, here are the components of the initial velocity vector. And then right here is theta naught, which is the unknown in the problem. Then we move through the entire path like so, such that we return to our original height. And then right here is the range x, which in this example is given to us, the value of x is given to us as 100 meters. The angle is what is unknown. Now, notice how the problem is phrased. It says at what angle or angles should the gun be aimed in order to hit the target? This is implying that there is at least one answer. In fact, there are two answers. Now, how can you aim the gun to ensure that you hit the target? For example, I'll use my meter stick to illustrate. Should you take the gun and aim it directly horizontally like so, such that the projection angle is equal to 0 degrees? No, because as we've seen in an earlier example, this then immediately means that the projectile is going to fall to the ground after traveling a relatively short distance horizontally. Instead, what we want to do is we want to take the gun and aim it perhaps at a slight angle like so for one solution, but then a second solution will look as follows. Imagine taking the gun and aiming it nearly straight up such that you could still hit the target at the same height at a distance of 100 meters away. If you can aim the gun like that and hit the target, more power to you, but ultimately there should be two solutions to this problem. Okay, let's go ahead and go through the solution. It's easy to do. Okay, what I'm going to do is take the range equation here and solve for the unknown, which is the angle. So let's go ahead and cross multiply the g and the v naught squared to the other side like so. Okay, now let me just go ahead and plug in the numbers there on the right-hand side of the expression. So the numerator is 9.8 times 100 and then divided by 380 squared. Okay, and then rounding it off a little bit, this is what I end up with. It's about 0.0068 about, like so. Okay, now think back to basic trigonometry. How many different angles have a positive sign 2? One in the first quadrant and one in the second quadrant. So, okay, I can imagine, for example, taking the gun and aiming it like so into the first quadrant and hitting the target. But how could I take the gun and aim it into the second quadrant like so and still hit the target that's over here? Well, not quite. Let's go ahead now and solve for the angle. But when I solve for the angle, I'm not solving for theta naught, I'm solving for 2 theta naught. So now I'm just going to go inverse sine on my calculator, and then 2 theta naught is about 0.4 degrees. Okay, what other angle has the positive sign? A second quadrant angle. In other words, the supplement of this value here. 180 minus 0.4 is 179.6 degrees. But is this the answer? No, and it's not the answer because this is 2 theta naught. What I now have to do is take each of these values here and divide them by 2 in order to get the answer. So now the answer is as follows. Theta naught, first of all, is going to be 0.2 degrees, like so. Okay, that's obvious. That's just a small angle directly above the horizontal. And now because I can't do this stuff in my head anymore, 179.6 divided by 2, that works out to be 89.8 degrees, which as you can see is very nearly straight up like so. Okay, so that's a very good application example of the range problem. As I'm doing these last couple of examples, I'm basically exhausting all of the details associated with projectile motion. There's really not much else to say about it except for one more problem. So go ahead and copy that problem down into your notes. It's different than the last 2 examples that I've done here. Okay, I'll erase the board here in just a moment, but let me read the problem to you first. At what angle must a projectile be launched from the origin, such as the range is twice the maximum height? So imagine a projectile and launching it, say, like so, and then right here is the range, right here is the maximum height, but we want to figure out specifically what angle I have to throw it at, such that the range is 2 times the maximum height. That's what's being asked for in the problem. Okay, let me do some erasing. Okay, we're not going to be using the range equation in this example. Instead, for this example, I'm going to need the following equations. The vertical position equation. I'm setting y naught equal to 0 immediately, by the way. The horizontal position equation. I'm setting x naught equal to 0 immediately, by the way. And a little bit later on in the problem, we're actually also going to need this expression here for the y component of the velocity vector. You'll see why as we get deeper into the example. Okay, so here's what's being asked. Okay, so we launch with some speed. And as we'll see, it doesn't matter what the speed is. Okay, here's the angle. The angle is the unknown. We launch from the origin. Okay, and then we travel through our path, like so, and then right here is the range. Right here is the maximum height, and then if you recall from an earlier example, when the object is at its maximum height, its velocity vector v is entirely horizontal. This then means that the y component of that velocity vector is equal to 0. Okay, another way of stating the problem is the following. Here's basically what we're given. We're given that the range x is twice the maximum height y. So we're looking for the angle specifically when this happens. So how do I even begin? Well, we are given this expression right here, so let's just go ahead and plug into it our expressions for the horizontal displacement and the vertical displacement like so. Okay, first of all on the left we have horizontal x. Like so. And then on the right hand side we have 2 times y. So 2 times this quantity here. Like so. Take a look at this carefully. As I wrote down this expression, however, I made a mistake. Take a look carefully at this expression. What was the mistake that I made? The mistake that I made was that I incorrectly kept track the times. For example, if I call the time from here to here when I reach the maximum height on the right-hand side of the expression t, on the left-hand side of the equation, this then means that I have to call the time from here to here, the range, twice as much. Because recall from an earlier example that when you cover the entire parabola, the time to do so is twice the value to reach the maximum height. So to correct for that, what I have to do is insert a 2 here in front of this time t, such that I can now write this expression correctly. This is the key to the problem. The remainder of the example is fairly straightforward. Okay, let's go ahead and simplify what I have here at this point. Okay, so I can cancel out this 2 and 2 here like so, and I can also cancel out a t from each term, like so. Okay, let me rewrite what I have at this point. Like so. And if you look at this expression here, you'll notice that there are 2 unknowns, the time t, which we don't care about, and the angle theta naught that we're trying to find. So what do I do at this point? Well, we have to get rid of the time. This is where the top of the parabola becomes important. As I noted earlier, at the top of the parabola, the velocity vector is horizontal, and the y component is then therefore equal to 0. That's why I wrote this expression down. Let's now set this equal to 0 and solve for the time t. Once I've done so, I plug it into the equation on the bottom board, and that then leads me to the solution. Okay, so let me go ahead and do some erasing. I don't need this stuff anymore. Like so. And now let's go ahead and write this here on the left-hand side as 0. There we go. And then solve for the time t. And it is the time t, by the way, from here to here. Remember, the time from here to here is 2t. So this is the correct time t. Okay, so move the gt to the other side, and then just divide by g. Doing those couple of minor mathematical steps at once gives us this. And now I'll take that expression for the time t and plug it into here, and watch what happens when I do. All right, so v naught cosine theta naught equals then v naught sine theta naught, and now minus 1/2 g times t, this guy here. Like so. And notice that a bunch of stuff cancels out. First of all, in the last term, the g's cancel, like so. And then notice that v naught is common to each term, so I can cancel that as well. And then all that's left are trig terms. Over here on the left, I have cosine of theta naught. And now watch this carefully. This is sine theta naught minus 1/2 sine theta naught for a total of 1/2 sine theta naught. And now let's solve for the angle theta by just doing a little bit of cross multiplying. I'm going to take the 2 and move it up here to the left, and I'll take the cosine and move it down here to the denominator on the right-hand side. Sine over cosine, if you recall, however, is tangent. And then therefore the answer is going to be the inverse tangent of 2. All right, so the inverse tangent of 2 in degree mode on my calculator is in fact about 63.4 degrees. Like so. So if you take a projectile and you launch it from the ground at a 63.4 degree angle, roughly something that looks like that, then the range x is always going to be 2 times the maximum height. Okay, this concludes the lectures and the examples on projectile motion.